Alright, so this is our Honors Chemistry lesson video for section 8.4, and if you thought the other sections were super long, this one is broken into 5 parts. Oh my gosh. So let's go ahead and knock out part 1 real quick. So one thing you probably will need during the 8.4 is you'll want a electronegativities chart. So if you're in my class, you have one in your packet. If you're just watching this online, then you can easily Google one. It's just called an electronegativity chart. So anyway, let's go ahead and get started since it's going to be 5 videos long. So covalent bonds involve sharing electrons between atoms. When the atoms in a bond pull equally, the bonding electrons are shared equally, so the bond is called nonpolar. So it's like a tug of war. They both want the electrons. And so it's like one atom's pulling towards it, the other atom's pulling towards it, and when they have equal electronegativity or equal strength, the electrons kind of remain in the middle. Think about the flag on tug of war when there's equal teams. However, sometimes when the atoms pull unequally, the bonding electrons are actually pulled closer to one atom, and that's when it's called polar. So sometimes when you have tug of war, one team's clearly stronger, so they pull harder. The flag in the middle stays closer to them. And so that's what sometimes happens in a bond. One atom is more electronegative, so it can pull the electrons closer, so it becomes what we call partially negative. Because it didn't actually gain the electrons, it can't get a full negative charge, but it becomes partially negative. And so then the other side, of course, is partially positive, and so we call that molecule polar because it has 2 poles, a positive side and a negative side. But remember, they're just partial positives and negatives. So when they're pulling equally and the electrons are pretty much in the middle, there is no partial positive or partial negative side, so that's why that type is referred to as nonpolar. So an atom's strength is measured by the electronegativity. That's where that electronegativities chart that I told you about comes into play. Because electronegativity is the ability to attract electrons. The larger the electronegativity value, the more strongly an atom attracts electrons. The more electronegative element gets a partial negative, so this symbol right here, it is just a lowercase delta, and it just kind of looks like an 8 that you don't finish, or you can think of it as an S where you went too far. Okay, so it's just lowercase delta, and it just means a partial charge, so it didn't actually gain the electrons. So the more electronegative elements get a partial negative charge, and the less electronegative element gets a partial positive charge. The greater the difference in the electronegativity between 2 atoms, the more polar the bond. So for example, here if you look at your electronegativity chart, C has an electronegativity of 2.55, F has an electronegativity of 3.98. So since F is more electronegative and stronger, it's going to pull the electrons closer, and so it becomes partially negative, and carbon becomes partially positive. And so again, because no one's gaining and losing, it's not a full negative or full positive charge. So it says determine the polarity of the following bonds. So we're going to do what I just showed you on that slide. Alright, so again, the numbers that I'm talking about, you're going to see me write them under each of the elements. These I'm pulling from an electronegativity chart. Alright, so H has an electronegativity of 2.1, Cl is 3.16. The more electronegative element gets the partial negative, and the less electronegative element gets the partial positive. That's all you have to do. Okay, so F has an electronegativity of 3.98. P, I think it's 2.19, yep, 2.19. So since F has the more electronegative atoms, it's partially negative, and P is partially positive. And so that's all you have to do to show the polarity of a bond, is look at the electronegativity values. Now, if for some reason you're not provided electronegativity values, then you would need to use the periodic trend that we learned all the way back in chapter 6. And so for the periodic trend, electronegativity increases as we go across and decreases as we go down. So if for some reason you had a question and no electronegativity chart is provided, you would need to use the periodic trend. And so then just a key fact to remember is fluorine is the most electronegative element on the periodic table. So as we get closer to fluorine, we become more electronegative. So just use that as guidance if you don't have a chart provided to you. Alright, So maybe pause the video, make sure you have electronegativity chart and try these. I'll assume you've done that. Let's look at them together. So Cl is 3.16 and C is 2.55. So since Cl has the more electronegative atoms, it's partially negative and carbon is partially positive. All right, and then we have O and S. So O is 3.44, S is 2.58. And again, these numbers are just from an electronegativity chart. Since O has the larger electronegativity, it's partially negative, and S is partially positive. Okay, so again, all you're doing is looking at your electronegativity chart to determine the polarity. And remember, the greater the difference in the two numbers, the more polar the bond, because we'll get to some questions about that. So a dipole moment occurs when a molecule is polar and has a partially positive and partially negative side. A dipole is represented by an arrow with a plus sign on one end. The arrow points toward the more electronegative element. So what we just did was we labeled the sides as partial positive, partial negative based on the electronegativity. If you're asked to draw a dipole moment, it's just an arrow with a positive on one end. The positive side goes with the atom that would be partially positive. The arrow points towards the atom that's more electronegative because that's the directions which the electrons would be pulled in. So if they ask you to draw a dipole moment, this is what they're referring to. All right, so let's look at how to draw a dipole moment. So again, the numbers that you're going to see me write are just coming from an electronegativity chart. So H is 2.1 and F is 3.98. So F is more electronegative, so my dipole will point towards the F. And I don't know if you're in my class, I'll just go and tell you I'm super picky about you putting that positive. If you don't put the positive, it's an arrow and I mark it wrong. If you're not in my class, then you'll just have to see what your teacher says. Alright, so sometimes instead of just giving you a bond, they will give you a molecule. If you get a molecule, there's a dipole on each bond. Alright, so we gotta draw our Lewis dot structure. So I'm going to follow my steps. H has 1 valence electron, but I'm going to multiply that by 2. O has 6 for a total of 8 valence electrons. Alright, so I'm going to draw and single bond everybody. The single atom goes in the middle, which is oxygen. I'm going to make everybody stable. Both my hydrogens have a duet, so they're perfect. Oxygen right now has 4 electrons, so I'm going to add 4 more. And then this becomes super important in dipole moments and polarity. You have to account for the shape. So if you haven't watched those 8.3 videos, go back and watch them, because water is not going to be linear. It is going to be bent, because those 2 lone pairs of electrons on oxygen are going to take up some space. Alright, so since water is bent, now I can do my dipole moments. So I'm actually going to have one for each bond, and then I can draw it for the molecule overall. Alright, so oxygen has an electronegativity value of 3.44. My hydrogens are only 2.1. Whoops, I wrote 21. 2.1. So my dipole moments are both going to point towards oxygen. And so that means in general, for the whole molecule, it's pointing upwards towards oxygen. That's important because we'll see later, sometimes the dipole moments cancel out. If they're pointing in opposite directions, they cancel out. And so even though a molecule might have polar bonds, the molecule itself may be nonpolar. Okay, so it's important to see that both of these are pointing upward towards the oxygen. So there is an overall dipole moment on water going upward. Now see, if for some reason we drew it as linear and we did it like this, it would appear that the dipoles cancel out. So that's why I'm saying shape becomes very important in questions like this. And even if they even give you the Lewis dot structure picture like that, I've seen that before, then you got to be careful and think in your mind, okay, they drew it as linear, but I know it's not really linear. Alright, so let's move on. Hopefully so far this is seeming pretty easy. Alright, so maybe pause it and you try to draw the dipole for both of these. I'll assume you paused it. Let's look at it together. Alright, so H is 2.1. S is 2.58, so since S has the greater electronegativity, my dipole moment would point towards S. Here, N is 3.04, H is 2.1, so since N has the greater electronegativity, my dipole moment would point towards N. So like I said, y'all, it's very important if you draw an actual molecule, every bond would need a dipole moment so that then you can see if they cancel out or add together in one direction. Just like I showed you in the water example. Alright, so next let's look at how to calculate the dipole moment, because right now we are just showing, which direction are the electrons being pulled. But now we're actually going to calculate the dipole moment. So whenever a distance separates two electrical charges of equal magnitude but opposite sign, a dipole is established. The quantitative measure of the magnitude of the dipole is called the dipole moment, and it's represented by mu. So mu equals Q times R. So mu is the dipole moment in debye, which is just a capital D. But a lot of times when you solve for this, you're going to end up with coulomb meters. But the question might ask you for the dipole moment in debye. So here is our conversion. 1 debye equals 3.34 times 10 to the negative 30 coulomb meters. Because coulomb is just our unit for charge. Q, you'll see in a second, is charge. And R is our radius or our distance. So it's going to be in meters. So when you solve for this, you're going to get the unit coulomb meters. But like I said, we normally use debye as our unit for dipole moment. So we'll just need to convert from there. Alright, so like I said, Q is charge, units of 1.6 times 10 to the negative 19 coulombs. That is the charge of like a one positive, like a one proton has this charge. An electron has the same charge, but it's negative. And the distance, of course, will be in meters. Alright, so let's look at what this looks like. So the dipole moment increases as the magnitude of charge that is separated increases. So as you can see, as charge increases, our dipole moment increases. And as the distance between charges increases. Now that's kind of weird because a lot of times we always say we want high charge and low distance. But we actually want a larger distance separating the charge, because if the charges are more separate, then there's more distinct poles, if that makes any sense. So like if your positive and your negative are just super close, there's not as distinct poles as if they're kind of separated, because then you have more distinct poles, which is what dipole moment is based on. So your dipole moment increases as charge and distance increases. So let's look at an example question, and then I'll let you try one. So it says the bond length in the HCl molecule is 1.27 angstrom. Okay, so I have my distance or my length, but the problem is it's in the wrong unit, because if you remember when I showed you the Q times R, R must be in meters. So I'm going to put myself a little note that I'm going to need to change that. Calculate the dipole moment in debye. So see what I told you? So we're looking for the mu, but we need it to be in debye, which is just represented by capital D. So I'm going to make myself a note. Okay, I'm going to get an answer. I need to change it to debye. That would result if the charges on the H and Cl atoms were one positive and one negative respectively. Okay, so again, a lot of times you're tempted to plug in the one positive or one negative for the charge, because that's what you think of. But remember what I showed you on the previous slide, our charge is going to end up being 1.60 times 10 to the negative 19 coulombs. That is our charge for a positive 1. All right, so let's go ahead and convert our distance so we can plug that in. So we have 1.27 angstroms. And so hopefully you remember that 1 angstrom is 10 to the negative 10 meters. So 1 angstrom is 10 to the negative 10 meters. So my angstroms cancel. And so, I don't know why I'm even looking at my answer for that. So obviously 1.27 times 10 to the negative 10 meters. All right, so now I'm ready to plug in. So I know that mu equals Q times R. So my Q, remember, since it says we're just having a full charge, we use our value for charge, 1.60 times 10 to the negative 19 coulombs times my distance, which we have changed to meters, and is 1.27 times 10 to the negative 10 meters. So once I multiply that, let's see, where's my answer? Up there it is. I got 2.032 times 10 to the negative 29. And if you look, coulombs and meters don't cancel, so my unit is coulombs times meters. But it's asked for the dipole moment in debye. So that's where I'll use that conversion factor that I just showed you on the previous slide. So 1 debye is 3.34 times 10 to the negative 30 coulomb meters. So see, the coulomb meters cancel out, and so I would do this number divided by this number. And so once I do that, I get a dipole moment of 6.08 debyes. So see, for this one, the only thing that's tricky is the converting and the remembering the thing about charge. So your distance has to be in meters, so if they give you angstroms, nanometers, picometers, those are common units you'll have to convert. Charge is not just going to be a simple number like 1 or 2. Okay, charge is based on 1.6 times 10 to the negative 19 coulombs. That indicates a full positive 1 or full negative 1 charge. And then just don't forget that when you solve this formula, your unit's going to be coulomb meters. So if they ask for debyes, then you have to convert from there. All right, so part B, it says the experimentally measured dipole moment of HCl is 1.08 debyes. Okay, so we got 6.08. But yet in reality it's 1.08. So boy, were we off. That's okay, we weren't off based on the numbers they gave us. So what magnitude of charge in units of E on H and Cl atoms would lead to this dipole moment? Alright, so what we're doing on this one is we're kind of working backwards. Here we have the dipole moment, we still know our distance, we're trying to figure out what's the charge. Because the whole thing is we already know it's not a full positive and full negative charge because they're sharing the electrons. Okay, so that's why our whole dipole moment's wrong. It's just going to be a partial positive and partial negative charge. So what we're trying to figure out is, okay, well then what is the partial positive and partial negative charge? Alright, so we're going to kind of work our way backwards here. So we know that, oh, I don't have much room over here, do I? Here, what I'm going to do is erase this top and I'm going to put my answer up here. I didn't leave myself a lot of room at the bottom of the board. Alright, so again, I'm doing this part B, I'm just going to do it up here. So we know that our dipole moment is our Q times our radius, but now we're trying to solve for Q. So I divide both sides by R, so my Q is my dipole moment divided by R. So I know that the actual dipole moment is 1.08 debyes, but the problem is when I plug into my formula, I need it to be in coulomb meters. So see, I'm going to kind of have to go backwards from what I just did. So I take my 1.08 debyes, and I use that same conversion factor that I showed you in the previous slide. Okay, so 1 debye is, sorry, I don't use this conversion factor super often, so let me figure out where it is right here. 3.34 times 10 to the negative 30 coulomb times meters. So see, you have to have the correct units to plug into that formula. So once I do that, I end up getting 3.607 times 10 to the negative 30 coulomb meters. And so that is a number I can plug into this formula. So I plug that in, so 3.607 times 10 to the negative 30 coulomb meters. And then I can divide by my distance, which remember we already changed it. I erased it now. We already changed it to meters, okay? And so it was 1.27 times 10 to the negative 10 meters. So if you look, your meters cancel. All right, so I divide, and I end up getting this right here, 2.84 times 10 to the negative 20 coulombs. All right, now this is where we're going to use this right here, okay? Whenever it says in terms of E or units of E, it means we want to take into account that 1 E equals this amount of coulombs. Okay, because we're trying to get a charge. We know it's a partial charge, so we're trying to get a decimal of a charge. So it's not a full positive 1, negative 1 charge. It's going to be point something. And so we can get that by converting right here. So all we have to do is say 1e is 1.60 times 10 to the negative 19 coulombs. And so see, then our coulombs cancel. And so once I solve, I get 0.18e. So in other words, instead of having a full positive 1 and a full negative 1 charge, there is a positive 0.18 and a negative 0.18. All right, and then it asks for H and Cl. Well, H is going to be the more positive one, so it would be positive 0.18e, and Cl, because it's the more electronegative, would be negative 0.18e. Alright, and so that one's all we got to do. Like I said, the math's a little tricky just because there's a lot of converting. So if you're not converting, or you're not good at converting, this formula is going to be a little tricky. However, if you love converting like I do, then you're probably great at these. Alright, so the next one, maybe try this one on your own real quick, and then pause the video, and I'll assume you've done that, and we'll look at it together. So it says, the dipole moment of chlorine monofluoride, which is ClF, is 0.88 debye. The bond length of the molecule, so I have my dipole moment right here in debye, so that's my mu. It says the length of the molecule is 1.63 angstroms. Of course, I know I'm going to need to change that to meters, though. Which atom is expected to have the partial negative charge? What is the charge on that atom in units of E? So in other words, you are doing what we just did on the previous slide for part B right here. You're kind of working backwards. Okay, so first let's do this part, because this part's super easy. All right, so we have ClF. So we just need to look at our electronegativity values. So Cl is 3.16, F is 3.98. So F would have the partial negative charge. So it would be F for that one. Alright, and so then it says, what is the charge on that atom in units of E? So this is where I'm going to work backwards again. Alright, so first I have to change my angstroms to meters. So 1.63 angstroms. And we know that 1 angstrom is 10 to the negative 10 meters. So that changes to 1.63 times 10 to the negative 10 meters for my R value. Okay, so we know that mu equals Q times R. We want to solve for Q, so I can divide both sides by R. So Q is mu divided by R. Now, of course, the problem is, again, they gave me my dipole moment in debye, so I need to convert that back to coulomb meters. So I'm going to grab that number over here, so I have 0.88 debye, and I know that 1 debye equals, oh, where's my number? Like I said, sorry, I don't use this conversion factor anytime except for literally right now, so I don't have this one memorized. Okay, so it's 3.34 times 10 to the negative 30 coulomb meters, and so once I multiply those two numbers, I get 2.939 times 10 to the negative 30 coulomb meters. Look, that's a times right there. Sorry about that. All right, so now I have my dipole moment in the correct unit. I have my distance in the correct unit, so I can plug it in. So my dipole moment is 2.939 times 10 to the negative 30 coulomb meters. And my distance is 1.63 times 10 to the negative 10 meters. So my meters cancel and I'm left with coulombs. And so once I solved that, I got 1.803 times 10 to the negative 20 coulombs. But notice it didn't ask me in units of coulombs, it asked me in units of E. So that's where we need to consider 1E is the 1.6 times 10 to the negative 19 coulombs. So 1E is 1.60 times 10 to the negative 19 coulombs. So my coulombs cancel. And so I end up getting 0.113E. Now the thing is, it says what's the charge on that atom. So it's talking about F. Well, we decided that F is partially negative. So actually putting this answer is not your final answer. It would need to be negative 0.113E. The partial positive one would have this positive partial charge. But since they asked us about the partial negative one, we need to make sure to include it as negative in our answer. Alright, so like I said, for the beginning part of this section, this is probably the hardest that it comes to. And like I said, it's just because some of y'all have a little trouble with all that converting. Gotta get good at converting. The faster you can do it, the better. Alright, so let's move on, and we're just going to talk about one more thing in this part. Alright, so as we proceed from HF to HI, the electronegativity difference decreases. Okay, so you can see the electronegativity difference decreasing, and the bond length increases. Okay, so see there's a difference in our electronegativity is going down, and our bond length is going up. Because the greater the electronegativity difference, the closer it kind of pulls those two atoms. Alright, and so then you can look also that our dipole moment decreases. Okay, because that electronegativity difference is decreasing. So when polar molecules are placed between oppositely charged plates, the partially negative side is attracted to the positive plate, and the partially positive side is attracted to the negative plate. So when the electric field is not on, all the molecules are randomly arranged. Once we turn it on, here's our positive plate, here's our negative plate. You can see now they've all lined up, and so they noted right here the white side is the positive side. So all the white positive sides are attracted towards the negative plate, and all the orange negative sides are attracted to the positive plate. So it just causes polar molecules to kind of align together. So the last thing that we're going to talk about in this lesson video is how to determine whether something is nonpolar, polar, or ionic. So bond polarity is determined based on the difference in electronegativity between the two bonded atoms. Whoops, sorry, it's the wrong version of 2. It should have a W in it. So when you subtract the electronegativity difference, if it's less than 0.5, it's normally considered nonpolar. Now, of course, it's still slightly polar, but for the most part, it's considered nonpolar. 0.5 to 2 is polar, and greater than 2 is ionic. So when you subtract, this is how you tell. So less than 0.5 is considered nonpolar, 0.5 to 2 is polar, and greater than 2 is ionic. So let's look at a couple of these. So it says, are the following bonds nonpolar, polar, or ionic? So again, all I'm going to do is use my electronegativities chart and grab a calculator. Alright, so I can see that N is 3.04 and H is 2.1. So I just subtract 3.04 minus 2.1, I get 0.94. So remember, I showed you on the previous slide, less than 0.5 difference is nonpolar, 0.5 through 2 is polar, and greater than 2 is ionic. Alright, so since 0.94 is 0.5 through 2, this would be considered a polar bond. And so that's all you have to do. Okay, here, this one's super easy. F is 3.98 minus 3.98. The difference between the two is 0, which makes sense because they're the same atom anyway. So this would be a nonpolar bond. Because obviously fluorine and fluorine have the same electronegativity or strength, so they're going to pull with the same force on the electrons. Alright, so the last one we have Ca and Cl. Now, you may have to subtract out of order. It's always going to be largest minus smallest because Ca has a lower electronegativity than Cl, so I'm going to start with Cl. So Cl is 3.16, and remember y'all, I'm just pulling these numbers from our electronegativity chart. And calcium is 1. So I get 2.16. So since my difference is greater than 2, it is ionic. Alright, and so besides, like when you're determining if something's ionic or not, besides just assuming it's a metal and a nonmetal, you can also subtract electronegativities to tell. Alright, so I'll give you a few to try, and we'll see if you get them right. So maybe pause the video, you try these real quick, and then I'll assume you've done that, and we'll look at them together. Alright, so we have H and Br. So Br is 2.96, and H is 2.1. So when I subtract, I'm going to get 0.86. So since that is between 0.5 and 2, it is polar. So hopefully you got that one right. Alright, next we have C and O. So remember, you always do largest minus smallest, and O has the larger, so it's 3.44 minus C, which is 2.55. And so once I put that in, I get 0.89. And so again, because that's between 0.5 and 2, it is polar. So hopefully you got that one right too. Alright, last one, we have Li and O. So O again is 3.44, Li is 0.98. So once I subtract, I get 2.46. So since that number is greater than 2, it is going to be ionic. Alright, so that is part 1 of 5 for 8.4. And so like I said, out of this first part, the hardest thing is going to be calculating that dipole moment. So just practice your conversions. It's not that hard if you just give a little practice.